Okay. Well, thank you. It's great to be here. And I have heard of BIDS, but have never been in this space or been into any of your activities. So it's a great opportunity for me to find out more about you. And I'm delighted to have the opportunity to share with you some of the work we've been doing. So again, my name is Therese Peffer. I'm the Associate Director of the Sustainability Infrastructure of Citrus. So this i4Energy was the old name, and we were incorporated along with water and transportation into this new name, this new initiative, which is Sustainable Infrastructures. I'm also the Director of an Enabling Technology Development Program at California Institute for Energy Environment, which is merging with the Berkeley Energy and Climate Institute, Becky. So I wear a couple of different hats. So what I'll be doing is, it's hard to describe all of the activities that we're working on. I'll just highlight a few of those and look forward to your questions. The basic idea, I'm academic staff. I conduct research in and manage research in energy-related projects on campus. So I work with people from the Lawrence Berkeley Lab, other campuses, UC Davis, and other researchers on this campus at UC Berkeley. A lot of my work, I was educated here, both in neurobiology and psychology as an undergraduate, and in architecture, building science for my PhD. And I tend to do research in buildings, user interfaces, so I still try to maintain both the psychology component as well as the energy-related component. And the goal of much of the research is to just create better comfortable environments for people, as well as reducing energy consumption. So the first project I'll talk about, this is going from sensors to electric grid. So starting off with the smallest component, sensors. We've been using wireless sensors in our work for a number of years now, and they continue to get lower in cost and higher in capacity and computation and things like that. There's one of David Culler's students in the software-defined buildings group right now is developing a very low power platform called Firestorm. I'm using a Raspberry Pi basically and adding a temperature sensor and carbon dioxide sensor on it. With these, if you distribute them around a building, you can start getting information about, gosh, how many people are in the space? Is the space occupied? Is the temperature appropriate for these people? And you can do a number of things. One is to make the spaces more comfortable for people, but also to, gosh, if you know that a lot of people are in the space, you can blow in some more air and make the room very comfortable in terms of, we've all been in buildings or in meeting rooms where it starts to get hot and stuffy and people start to get sleepy. Well, if you blow in some fresh air, often that can solve that issue. I'm also involved in a project developing a low-cost anemometer. The anemometer is basically, it detects airflow and air volume. And the idea is, if you can put this in a space, in a fume hood, in a duct, you can detect the amount of flow that's going to a space, and again, optimize to make sure you're getting the right amount of flow at the right time, and again, save energy. Another project I'm working on with Carnegie Mellon University and the Silicon Valley campus is to look at if you provide sensors at a distributed level. A lot of times we have building energy monitoring at a whole building level. The idea is, if you can start looking at zone levels, at room levels, one, you can provide visibility to people, how much energy you're using for your computer, your monitor, your fan, your heater, whatever, and also give that visibility to the facilities manager so they can start saying, gosh, everyone in that space is cold, they're bringing in their heaters, that sort of thing. So we've been doing a number of different projects in this space. Another project, this was funded by the California Energy Commission, called Changing the Rules. It's also based at the Center for the Built Environment across campus in architecture. The idea behind this is to develop occupant-responsive building controls. And so the idea here is they have a personal comfort system. It involves a foot heater, a personal fan, but also this chair that can provide heating and cooling directly to a person. And we also have this web-based application that it can poll for occupant satisfaction. Are you too warm? Are you too cold? But they also allows people to get control over their local environment. And so what we're doing is integrating these two so that you have information from the building automation system in a large office. People have control over their local space with these chairs and this application. And we're just seeing, again, can we keep people comfortable? Can we save energy through this system? A project that, again, David Culler's software-defined buildings group across campus has been working on for a number of years is a platform. Once you have these sensors, once you have this data from many different sources, whether it's interval meter, whether it's a building automation system, or what have you, to bring all that aggregation of time series data into a single database. And so this platform has been developed really over the last 7 years. We'll be using this platform in a project that'll start in a couple months. We're working in conjunction with the Transportation Sustainable Resource Center on campus to look at electric vehicle charging and homes. So once you can combine interval meter data from whole home data, thermostats, lighting controller, this is the Internet of Things, right? But also combine that with electric vehicle charging, you can start doing things like balancing loads. You can start looking at, say, if they have a photovoltaic system on their house, to start balancing load with supply. We're also looking at aggregating a number of houses into a neighborhood and start looking at a neighborhood aggregation, looking at that scale. So this is the Extensible Building Operating System Services, XBOSS, and then /V is, we're looking at using this for electric vehicle charging. Another project that'll start in a couple months is it's led by the Electric Power Research Institute down in Palo Alto, but we're subs on it, is designing thermostats for low-income households. And the idea here is looking specifically at this population and, gosh, what do they need? What are their, what are some barriers? What are some of the issues with this population? Do they need a different kind of user interface? Do they need a different kind of, a simpler control? My dissertation was on thermostats, so I know a little bit about this area and how most people can't program or don't program their thermostats. Nest is a nice example of a learning thermostat, but even with that, I've heard many stories of people not being able to use their Nest properly. So that's what we're going to be looking at here. We're going to spend a lot of time just looking at what are the issues and getting to know this population better, and then trying to design a very low-cost solution so that we can, again, make sure that people are able to use their thermostats, get the thermal comfort they need, but also save energy. Another project done, this was done in conjunction with Lawrence Berkeley National Lab. A colleague of mine is working on this scoping study to look at direct current DC power integration with the goal of these zero net energy, that's the goal, is to reach that. And the idea is that a lot of the renewable energy sources are direct current, like photovoltaics, and a lot of the loads inside your house or in your office, but this is more looking at homes, are supplied by direct current, right? We see the transformers for our computers, our monitors, small motors and things like that. So what they're looking at in this study was looking at, well, gosh, why can't you just use that direct current power supply directly into the house for your loads, for your direct current loads? And then this is the last project I'll talk about. The micro synchrophaser project. This project has been going on for about 2.5 years. It's in its last few months of operation. The idea here is you have a device that can measure the phase angle of current or voltage. And it's high resolution. You get like 10,000 points per second. And it's time synced, so you can have two different devices at a distance away. And what you can do with this is that you can start looking at, gosh, when the voltage starts to dip, what can you do immediately to help out? They're actually still looking at, with this data, trying to figure out the different applications they can use for it. But that's at least one that they know right away that they can, if you start seeing changes in the voltage very quickly, then you can do something about it with this information. So, and this is looking at microsynchrophasers for the distribution grid, not for transmission side. So that's what I brought to show, again, going just from sensors and then all the way across to looking at some user interface stuff and then looking at the big picture of the utility grid. So I think with that, we can have a discussion. I'll take your questions. Thank you.